So I'm going to briefly go over how your semicircular canals work and how your cupula and how hair cells correspond to detecting changes in rotation. Okay, so angular acceleration. So if we were to turn your head left, let's say, so you're rotating your head left, and this is your rotation speed right here, we'd see a depolarization back to baseline levels and then a hyperpolarization once you finish turning. And I'm going to try to explain in pictures why you actually see that. So to briefly go over the structures, what you see here, right, is your hair cell, which has cilia embedded into your cupula, and then ultimately it's in this ampulla. And you have the semicircular canal, which again is filled with this thing called endolymph. All right. So in terms of the hair cells themselves, when hair cells depolarize, so depolarization is if your hair cells bend this way towards the highest point, okay, and this is the kind of cilia. So when they are stretched this way, you have depolarization. When they're stretched this way, so they're stretched this way, then that's hyperpolarization, okay? So let's go back to rotation left, okay? So basically your head is turning counterclockwise. So what's happening then is, let's say you have your endolymph, and this is a cartoon of the semicircular canal when we're turning left. So your body, or your head actually turns, right? So your head is turning, and you have this endolymph, and that's actually stationary for a little bit longer. There's this delay in terms of how long it takes for your endolymph to actually also start moving and rotating counterclockwise. So your head will turn, and that will bend. You see that? It'll bend your cilia, and that will cause depolarization. All right, and that basically explains this part, right? So you start rotating, you see depolarization. Eventually, your endolymph will also catch up in terms of the angular acceleration and the velocity at which it's moving. Okay, so you're going at this rate. Your endolymph eventually also goes at this rate. Now, what's interesting is at a certain point, your head and your endolymph, okay, they're moving at the same velocity. But then ultimately, all of a sudden, your head stops rotating, right? So your head stops rotating, but it takes a little bit longer for your endolymph to also stop moving because it's a fluid, right? So it's going to keep going, and then it's going to slosh around, and ultimately it'll return to the same velocity that the head is at, which is no velocity. But before that happens, the endolymph will actually keep moving in that counterclockwise direction if we're moving our head left. And what happens then is that your endolymph will push, you see that? Your endolymph will push your stereocilia towards the opposite direction, which is going to cause hyperpolarization, which is what we see here. Now ultimately, your velocity of your endolymph and your stereocilia, ultimately your cupula and so forth, they're going to stop moving. And it'll return back to normal baseline levels. Okay, so your fire rate returns back to baseline after a certain point. So this is all about turning counterclockwise. Initially you get a depolarization, no change while they're at the same velocity, and then ultimately hyperpolarization. And this, again, is in regards to the left semicircular canal. Okay, if we're looking at the right semicircular canal, it's going to be the opposite pattern. So something like this right here. All right, so this is the left canal, which we just talked about. This is the right canal, so it's the opposite pattern.